It's my pleasure to introduce Professor Luis Pineda from the Department of Computer Science from the Institute of EMAS, Applied Mathematics and Systems Research of the National Autonomous University of Mexico in Mexico City. We've known each other for a long time, since I think at least 2012 or so. So it's been a decade now, actually. So this is like a decade anniversary or something like that. We were working in the same department. First, I don't know, as a postdoc, and then as a faculty member over there. And we've always had a lot of conversation about the relationship between AI and consciousness and the mind. And we noticed that we have some overlapping interests in terms of moving away from the kind of classical Turing machine style of looking at the mind, and moving into territories that are less deterministic. And so we've kind of developed those lines a little bit independently. Luis may be coming a little bit more from the area of the theory of computer science, and me more from the area of the theory of biology. But there are some interesting connection points that we always wanted to explore more. And so hopefully with these seminars, we get a chance to delve a little bit deeper into these ideas. So without further ado, Luis, please, we look forward to your presentation.
Well, thank you very much, Tom, for the invitation, and Tesh for coordinating the logistics. I really appreciate it. And I'm really glad to have the opportunity to talk to you about the work on the entropic associative memory that I have been developing with my colleagues and students over the last few years here in Mexico. And I go straight to the talk. And can you see my slides, correct? Right?
Yes.
Okay. Well, in this session, what I'll try to do is to give you a very informal and intuitive overview of the ideas underlying the entropic associative memory, kind of even a bit metaphorically, just to get you the feeling. And the idea is that in the next session, we can talk about the actual experiments and algorithms and results. So, and the first here is I like to give you a general definition of memory for the purpose of this work, which is just a memory is a functional system that allows registering and storing information to be recognized and retrieved later. This is a kind of very, very general statement. And here the opposition, of course, is between declarative memory, in which information is stored to be retrieved later, which is usually considered symbolic, and where the things that are stored there are facts or imaged, and we think of terms of learning. So this notion of storing information in memory is learning in a very traditional sense. And the opposition here is to procedural memories, in which information is used for training, so training the memory. And these are usually considered sub-symbolic systems. And instead of getting back the information that we store, the point is to acquire abilities like perceptual and motor abilities that can be best perhaps thought as transfer functions from the input to the output. And one property that is pretty salient in natural memory, from my point of view, is that it rejects cues to objects that are not contained or stored. And this directly without search. So for instance, if someone comes into this room and I've never seen him before, then I know that immediately. And I reject, I know that. Or if someone says a word, say in English, that I never heard before, I know that I don't know the word, and I do that somehow without search. And this is very important because if if we had to test all hypotheses that are around, well, it would be a very costly operation and heavy, with a low, very heavy computational load on cognition in general. And one antecedent for this view, for the memory that I have, is the work of Frederick Parklet in his book, Remembering, Study in Experimental and Social Psychology, that was published in 1932, pretty long time ago, where what Bartlett did was to ask his subjects to register short stories or drawings, and then he asked them to recollect the stories just immediately, and in an hour's time, in a day time, a week, a month, a year, 5 years, and there were some subjects that were followed even for a few decades. This was a very long-term longitudinal study. And the conclusion that he had, of course, was that the memory was associative. I mean, the cue is central to the recovery of the object. But also, I mean, what was recovered at the end, especially in the long term, was not a photographic picture of the initial stimulus, but rather an abstraction that had to do with what was the situation about. So people knew that the aboutness of the recollection, although everything else could be changed and a lot of information could be lost in the process. So these are this important component of abstraction. And also the recollection was always a reconstruction. It's never a photograph or what was recorded originally. And soon afterwards, in 1936, Turing presented the general model of the Turing machine in his paper about computability. And in this machine, that is the general model of digital computers, that is still the main model of the universally accepted model, I mean, there is a notion of memory. And this notion of memory has to do with there is a tape in the machine where there are cells, and there are symbols written on these cells, and there are strings of symbols written on this. And what an algorithm does is just to change the string in the tape at the initial state of the computation and replace that for another string at the end state of the computation. That is the memory. Okay, and if you think a little about it, what this memory, the memory in Turing machine, what do represents is printed text. I mean, the traditional printed text. So there are types in the press, and then with that, there are books produced, and in general, this form. And the purpose of this, of text in general, all over, is communicating, recording, and supporting calculation. And then the text is a material representation of language. And it does require a physical medium, like the piece of paper, the vocabulary of symbols, and set of composition rules to define the strings. But the most important thing that I like to highlight here is that this is an external representation. Text, written text, is an external representation. And that is the object that is modeled in the Turing machine. And then when von Neumann introduced the von Neumann architecture and the random access memory, that is the standard memory that we use in computers to the date, I mean, it's the same. I mean, these random registers model this external object, the text, and with that we do computations all the time. Okay. So all computing, I mean, it doesn't matter what kind of object is being computed, is a textual representation of the object that is interiorized. So the external representation becomes internal in computer machines, but by design, because we design computers to do that in the first place. And but this kind of memory, the internalization of memory, is quite different from the object that it would be required to support the memory operations in Bartlett's sense. I mean, these are very different kind of objects. So for digital technology, it's okay. We can have these representations, but we think of terms of mental functions. I mean, it's very hard to think of representations in that way. And that was one of the points that was stressed by David Romelhart, and with the foundation of the connectionist movement and the late 70s and early 80s of the last century, and the parallel distributed processing group that they had at the University of California in San Diego. This book was called Explorations in the Microstructure of Cognition. And in the introduction of this book, Romelhart is pretty clear that one of the reasons motivating this approach is precisely the failure of the Turing machine or symbolic computations to model mental processes, and in particular, associative memory. It's limited to that. And in this program, and one of the prominent members of the group was Geoffrey Hinton, that probably you know of him because he's probably the leading figure in deep neural networks. He was awarded the Turing Award 3 years ago. And in this book, in one of the chapters that is called Distributed Representations, he makes a very interesting distinction between local memories and distributed memories, and local representations and distributed representations. And the point is that the local representations, I mean, the relation between the memory partitions in the machine is one-to-one with the objects that are represented. So there is a partition of memory for representing one object, and there is a partition of memory that represents another object, and these partitions do not intersect. While in distributed representations, this is not the case. So the partition that is used for representing one object overlaps with the partitions that are used to represent other objects in a many-to-many relation. And in addition, and this overlapping somehow is what allows the associations, because the units are shared and that represent the connections for the different concepts. And in addition, a distributed representation generalizes in the sense that the objects that are input to the representation interact, and as a side effect of these interactions, there are novel objects that are created in the representation that may be of members of the same class. And this generalization property is essential in neural networks that generalize. So you train with one particular set of instances, but then when you test, I mean, the entities using the test need to be, I mean, different from the ones that were used in the training. So this is the generalization. And these are these two very important properties of distributed representations. And very soon afterwards, John Hopfield in Princeton developed a memory, associative memory within the framework of neural networks. And he conceived memory as a dynamical system, like physical systems that are dynamical systems. And in his conception, what the neural network represents is an energy function in which the local minima correspond to the patterns that are stored. And there is a local minima for each pattern that is stored in the memory. And the memory is used presenting a pattern to be sought, and then this pattern is retrieved from the memory in the neural networks paradigm. But now, if we contrast the putative properties of natural memory with the properties of symbolic memories and Hopfield memory, we have some dimensions that are important, where the memories are associative, where they are declarative, where they are distributive, what are the properties of the retrieval operations, what kind of negation is implemented in the systems, and what kind of processing. And of course, natural memory is associative. Symbolic memories are not associative. They are addressed by numbers, by directions. Hopfield memory is associative. And About the declarativeness, well, natural memory is declarative, RAM memories are declarative, what we put is what we get, and hopping memories are usually considered not declarative because they are sub-symbolic. Although there's something to be said about that. About the distributed property, natural memory is probably distributed, and RAM memories are not distributed, are local, and hopping memory is distributed. And about the retrieval operation, natural memory is constructive, but RAM memories are reproductive, because what we input into the memory is what we get. But somehow paradoxically, hopping memory is also reproductive, because what we recover are the patterns stored exactly in the local minima of the energy function. And the point of the memory in that framework is to recover a pattern on the basis of a full, complete, or perhaps an incomplete queue. And that's the way these memories work. So in that sense, hopping memory is unlike RAM memories. It's not constructive. And it's unlike constructive memories that are natural memories. About negation, well, as I said, natural memory implements a direct negation. But in RAM memories and hopping memories, negation is done performed by failure. So one has to search in the memory in order to find out that an object is not there. And somehow they implement negation by failure. They say, I don't have this because I failed to find it. Or probably in the hopping paradigm, instead of getting the object, the memory returns the closest object in Indier's energy function. But that's a mistake. Essentially, it should be a false positive because it's not the object that results. It's just an object that resembles the memory. So pragmatically, it might do the job, but nevertheless, it would be a mistake. And about processing, well, natural memory is most probably parallel. RAM memories are fundamentally serial. And hopping memory is serial and parallel because essentially the representations are presented as matrix of numbers. And matrix operations have a serial part and a part that can be parallelized, and that resides the parallelity of these memories. So with all this, I mean, the question for me, when I was thinking of this problem, was whether it was possible to design a computer memory that resembles better the putative properties of natural memory. And I say putative because we really don't know what are the properties of natural memory. It's a big open question. And then from this came the entropic associative memory. And the format for the memory is a table, an array, a standard array. It's not a network, it's an array. And these tables, the columns represent attributes or features of objects, and the rows represent values of these features. And objects are represented by functions in which there is a mark or a value assigned to each argument in the table. So functions represent objects. That's the basic idea. And so the object of computation here are the functions. So for instance, if I had this function, suppose that this function represents a dog, this object, okay. And another function, let's say this function, which is a different one, represents a different kind of dog. Okay. So the first intuition is that the overlapping these two representations represents both dogs, and this is the abstraction of the two dogs. But now, this object is no longer a function, it becomes a relation. But the important here is that the presentation is distributed because the same marks in the table contribute to the representation of different objects. So there's a distribution property there. And there is also a productivity in this disjunctive abstraction that I'm presenting here. Is like the generalization in neural networks. And you can look at this in this way. In a latent state, when we have introduced these two objects, The memory, I mean, all the marks, like I said, are in the background. There is no one particular figure that I'm looking at. So if the memory is not being observed, nothing is being registered or retrieved, it's latent there. Okay. And there are many possibilities of object represented, but we do know which one are. So if I highlight this function and left the other in the background, there is the representation of this dog. And I highlight the other function and left these marks in the background, well, there is the other representation. But in addition to that, there is a productivity because there are more functions in the table than the one that were introduced. And what do they represent? In this case, this is one, and this is the other. Okay, so there are 4 functions that are overlapped, 2 of which are the productivity of the memory. And the object itself, the memory itself in this latent state is an indeterminate object. It's indeterminate, everything is latent. And it's unconscious. So the memory is not, we do not think about any particular object, but just think of the whole of the object at the time. And this is important because if we had to think of all the objects that are in memory at a particular time, that would be an overwhelming load. So it's essential that this information is somehow unconscious in this latent state. And then, as any object that is indeterminate, there is an entropy associated to it. So entropy, as you all know, is a measure of indetermination. And in the memory, in the entropic associative memory, the indeterminacy or the entropy is measured at the average indetermination of the values assigned to the arguments in the distributed representation. In a sense that there are several values for each argument, it's indeterminate which one we choose the moment we recall information from the memory. And the entropy is measured by this formula in the basic form, where here xi is the inverse of the number of marks in a column, just simply the inverse of the marks in the column. And this term log of xi is then the number of bits that measure the indeterminacy of the corresponding column. And the entropy is the average of all these indeterminacies. So we have this overall measure of the indeterminacy of the memory at a particular state. Now, if we think of these arrays, the maximal capacity or the largest number of functions that can be stored in a table is n, the number of arguments to the power of m, which is the number of values. Yes, because there are the possible combinations that we can form with the objects. The time we can combine the objects in the argument, the first argument, and the second argument, and the third argument. So this n to the n. Okay, and in this particular case, the entropy, it happens to be 1.5. And the current number of functions that are stored in the memory is just 2 to the power of the entropy times the number of arguments, which in this case is 2 to the 1/2 to 4 times 4, which is 4. So which is the number of functions that are stored in this particular memory. And this number, you can imagine that it's a pretty large number. If we, in the experiment that we do, these tables have, in the basic experiments, 64 arguments, 64 columns and 64 values. So n is 64, and the entropies are in the order of 5, 6 for the domain we have explored. So this is 2 to the 4, say, times 74, which is a huge number. Okay. So when we, and this is huge in relation to the objects that are actually stored. And this has pretty interesting consequences that I talked about it later. Well, this is the overall setting of the memory, and now we have to define the basic memory operations, which are three: the register, memory register, that we call lambda, memory recognition that we call eta, and memory recovery or memory retrieval that we call beta. And alpha register is just the inclusive disjunction cell by cell between the memory. Suppose that this is the memory state I, we have this dog, and there is an auxiliary register in which the cues to the memory operation are placed, and which is also used to place the objects recovered from the memory in the memory retrieval operations. So in the basic case, suppose that what memory is at this state, the cue to the operation, which is a register operation, is in the auxiliary register, and then there is a cell-by-cell disjunction, the inclusive disjunction between the cells. And then that is the way the overlap is made and the function is enriched. And of course, these operations can be applied systematically, and suppose that we have the memory in the new state, and now we have a new object, in this case, a rabbit that is in the auxiliary register, and registering is performing the same operation and enriching the state of the memory. And then with this, there are more marks in the table. There are more objects contained in the table, and the entropy of the memory is larger. So there is a larger amount of indeterminacy in the memory. And this does represent the abstraction. So the memory represents the abstraction of all individuals that have been registered at any moment of time. And the eta recognition is implemented directly through the logical material implication, which is the inclusion relation. So if I have this cue, that is this dog, and I want to see whether it is included in the memory in this particular time, then the computation this performed is the if operation. So if all the cells are included, then the operation is accepted. In this case, it is the case. It's just inclusion, the common intuitive notion of including something in something larger. But if we have a banana here, for instance, and the signature is this one, that is a function as well, then I can see that there are marks in the signature of the banana that are not in the memory. And if there is at least one of these in which the cue is on, but the corresponding cell in the memory is off, then material implication is false. And then if there's one of these at least, then the cue is rejected. So then memory rejection is performed directly by this inclusion test in one single computational step, and there is no search involved, which is a very important property. And finally, beta retrieval or recovery is defined like this. If the cue is included in the memory, and you will assess that through the eta operation, then select a value for each argument of the memory randomly, according to a distribution centered on the cue. So in this case, suppose that this is the memory, this is the cue to the memory retrieval operation, the cue is accepted, and then the retrieval operation selects for each column one particular argument that is included in the cue. And in this particular, in this example, the argument that is selected, the value is exactly the argument of the cue. And the object is recovered kind of in a photographical fashion. It's a picture of the object, a recollection. But of course, it is defined, the operation is defined randomly, then with the same cue and the same memory, then other objects might be retrieved. In this case, one object is the cue, but the other three arguments are different ones from the cue, but are included in the memory, and then an object is returned, and this situation it happens to be in this example for the illustration, that is the representation of the rabbit. So then, through the cue and the memory, we get an association by the operation. And of course, this operation is bidirectional, and the rabbit might be used to recover the dog as well. But even further, as the operation of retrieval is random, is it also possible that the cue is accepted in the memory, but the selection of the arguments, as they are random, they might get a function that is not one of the ones that were explicitly input, but one on the productivity of the memory. One of these vast number of functions that are there by the side effects. And it happens in this case that it happens to a new kind of block that was never registered before. Okay. So, and this is like imagination. So it's an object that is produced by the memory in terms of the state of the memory and the randomness in the operation of selection. And this is kind of a metaphoric, like an accident in genetic recombination, that we get these objects that are novel because just these accidents in the way the information was recovered from the.
Sorry, Liz, can you go back to the slides? So the reason why this is imagination is because there's a check mark appearing that wasn't existing before, or?
Because, I mean, it is in the productivity of the memory, but it wasn't recorded before.
But it has to be a combination of previous check marks. I mean, it's not like a new check mark will suddenly appear that was never there before.
It's there. So when as fed objects are recorded in the memory, there is this vast productivity there that I mentioned, this huge number of objects. But there are just potential objects, okay? And there are so many that most of them are not even real, probably. But some of them might become real. So the point is that the way the recall is defined, the memory retrieval is recalled, this object can become actually recovered, and then they might be confirmed by external evidence somehow.
So this is kind of, wait, sorry, maybe just paraphrase it. Are you trying to say that something like a spurious attractor in a Hopfield network could be considered as a, imagination? You know what I mean? Well, so you usually train it with all these images, and then, you form an attractor for each part of the training set, but sometimes the overlaps create spurious attractors that have never been actually presented. So is the idea that those spurious attractors could be something like the imagination of the system?
Well, but normally, I mean, in Hopfield memories, the local minima, the attractors correspond that the objects are used to train the memory.
Right.
And then when you select these objects, then they are recovered exactly. So in that sense, there is no truly generalization of Hopfield memory.
No, but sometimes it creates like, by accident, new attractors that.
Right. Well,
those are the spurious ones that. Anyway, okay, maybe you can just continue. I just wanted to.
Yeah, you can talk
it is the overlap. Okay.
Right. Okay. Yeah. Okay, the next operation that is defined in the memory is the relaxation. And this is useful because sometimes the cues are not complete. For instance, in this case, we have the cue that is occluded, or they might be pretty noisy. And then the representation in the abstract future states might not be complete. I mean, might be some errors on some attributes. So for instance, in this case, the representation might be these red marks represent that they are erroneous because the lack of information. But we have, in the experiment, we have said that the structure that is in the memory there provides the right features for a very number of values, and there are just very few that are, let's say, wrong ones, and then we can relax, I mean, the test of the material implication. And instead of requiring that every single mark is included in the memory, we can relax some of the columns and then still accepting that. So in this case, suppose that this is the marks, and when these cues with this particular partial information, the memory operation retrieves nevertheless the right object, okay, through relaxation. But of course, it might retrieve another object because there is partial information, and summing this up to the random nature of the retrieval operation, it might be a similar object by association, or it might be even noise as well. But the point here is that the beta operation is always a function that has the Q as arguments and retrieve an object that is a construction. That is a construction in this random sense. Of course, this is a construction that is made from the space of the productivity of the memory. In that sense, is there. But nevertheless, it has to be realized in order to become an object there. And this construction goes from the recollection, that are kind of photographical images, to the associations that are related, to the imagination that are novel, to noise, because there are also information that might be just not, might be not informational at all. But the point here, I mean, in any case, the actual retrieving information from the memory determines the object. So in the latent state, the passive state of the memory, the information is indeterminate. But the moment it gets selected, then it gets a fully object. We get a fully concrete determined object. And this is a process of interpretation. So interpreting renders an object, and also this object, when it's interpreted, may become an object of consciousness. And I like to have this example of this process with this figure that you may know. It comes from the philosophical investigations of Wittgenstein's. And if you don't know the figure, probably you don't see anything at the first time. It's an indeterminate thing. Okay. But if you keep looking at it, suddenly you might realize that it's a dog looking leftwards. Right? So the moment you see the dog in your mind, there is an interpretation and you are conscious of it. But this figure is quite unstable. These ambiguous images are quite unstable. And then maybe suddenly you realize that there's a rabbit looking rightwards. Do you see it? Do you see the rabbit? Okay. But this is kind of unstable, and this cue might also inside again into the memory and might render the next time the dog or the rabbit again. Okay. So, and this process of rendering the information is the process of making the interpretation. In that sense, there is the conscious impression in the mind. So it's like Schrodinger's cat, that the memory is indeterminate. What is there in the memory, I think by necessity in long-term memory, is indeterminate. But when things are observed, they become determinate and then conscious. And overall, the memory follows what we call the entropy trade-off. And in this graph, I mean, in order to be able to recall information from the memory, there must be information in the memory. So the memory is empty, but nothing could be recalled. And along the use of the memory, there is and registering information, well, the increased information is there, and this is reflected here, and we have a corpus. Here is a corpus of remembered information, and this axis represents that here we just have 1% of the corpus in the memory, which is almost nothing. The memory is practically empty, and then we increase the portions of the corpus that are included, registered in the memory, 2%, 4%, 8%, 60%, 32%, 64%, and 100%. So this is when all the corpus is there in the memory. The memories are full with the corpus. Of course, the memory can have much more information depending on the size. And this amount of information, I mean, reflects in the entropy of the memory, which is the average indeterminacy of the columns. So you see in this particular example, it goes from 1.6 to 3.4. And now what happens when you recollect information at different levels of entropy? So if the memory is quite empty, and nevertheless a cue is recovered, then there is very little information, but the recollection is pretty precise. It had to be very close to the signature of the object that is stored in order to be recovered. So the precision is very high. But as there's no information in the memory, many cues are going to be rejected. There's nothing there to be matched for. So according to the memory is enriching, so it's increased, then there are more information in the memory, and then cues are more likely to be recovered with still some degree of precision. But there is a point, I mean, in which now this is operational register, but suppose that we have more information, then imagine that the graph is completely filled with marks, then everything is going to be recovered. And memory recall is 100%. But then if all the cells in the grid are filled, then when you recover it, it's just kind of a random thing. I mean, it's noise. So then the precision starts to decrease. But there is a range of entropies values in which there is a very good compromise between the recall of the memory and the precision of the memory. And this is something that happens very regularly in the experiments we've done and in other aspects of the rationality that we have been studying. Now, something that is a little beyond the actual paper is this aspect of learning, because if cells are used often in the recollections, these cells should have a larger value than the cells that are not used often. So in a sense, the recollections that are performed that are often, then the value of the cells sort of increase. So if we have this learning aspect in the memory, so instead of having the memory like a flat board, like a chessboard in which there are zeros and ones, then the memory becomes a kind of a landscape in which in every square there are towers that represent the strength of the memory, and then they might have an impact on the recollection. That larger towers or highest towers are more likely to be selected in the memory recollection operation. Another aspect is the affectivity. I call here this lambda affectivity, for considering the fact that registering information that has an emotional content should be strengthened in relation to memories that have no essential content. So then it's at the same, I mean, if the recollection has this emotional value, then the cells should have, that are related should be increasing the strength value. And the other way around for the beta selection, I call beta affectivity, in the sense that the degree of randomness that is allowed in the beta recovery operation depends a lot on the interest that we have. I mean, so if we're interested in getting a faithful recollection of the object, well, we want to have a small randomness in the selection process. But if we're interested in making association, we can kind of allow a more randomness, like opening a valve a little more in order that the associations are permitted. And if we are in the field of imagination, we can just open the whole valve to get a fully random press to see what we get. Okay, so this is another aspect. But in any case, I mean, the recollections considering these weighted values and the randomness allowed in the beta operation go nevertheless from the recollection to the association to the imagination to noise. And this had to be reflected in the definition of the memory operations. So in the work that we're considering now, I mean, we are considering additive lambda register operations in which instead of just having the disjunctive union, we can have a value for the cell that is increased and the affectivity parameter. The relaxation is a parameter of the eta recognition, so the amount of relaxation that we want to allow in order to accept an object. And of course, if we have this, then the better retrieval operation has to take into account the weighted values in a random fashion. Weighted things are more likely to be recovered, and the affectivity parameter. And this also changed the entropy, because if they are weighted parameters, then the amount of indeterminacy of the columns in which there are weighted cells diminishes the indeterminacy of the column, and then diminishes the indeterminacy of the memory as a whole. Okay, so this is the overall picture, and I think I can stop here for today. And we can talk about, this. You have any questions or comments, or you disagree strongly in something or in everything, well, be my guest. I'll be happy to try to answer to the best of my abilities. So.
Great. Thank you so much, Luis. I think, I very much appreciated especially your kind of, deep historical approach to your project. I think that's going to be also very useful for our students to learn more about the history of computer science and where all of this is coming from. I think, I guess the idea is that this was the kind of background framing for the model that you're going to present to us next. So, I have questions, but I feel like, they might probably be better addressed to when we see the details of your implementation and talk more specifically about the technicalities. But yeah, there's I guess the general idea of, that the memories are, somehow intrinsically indeterminate and then take shape during the process of recollection. Yeah, makes sense to me. Do you find that this is an unusual position to take, or do you feel like I say, someone like the psychologist studying remembering would disagree with you there, or would they say, well, this is exactly what we're trying to say too?
Well, as you know, memory is a huge field of study in neurosciences and in psychological studies and in computer science. So. Well, I mentioned the work by Bartlett that is seminal. It's a seminal work in the studies of memory, and I think it's consistent with the modern views. But of course, the studies of memory in general in neurosciences, are more directed to the structural, anatomical, and functional areas that are involved in memory, but they don't really provide models of how the information is actually stored or registered or maintained or retrieved. It's very silent on that.
That reminds me, you're bringing in neuroscience. So one thing that we've been discussing in our unit is the work of Walter Freeman, who studied olfaction in the rabbit. And this is like, a couple of decades ago, but one of his key findings was that even for the same stimulus presented over time, the activity of the olfactory bulb in the rabbit brain it continues to drift, and it's not the same over time. And this was recently, rediscovered in a paper in Nature, where they call it representational drift. I think he called it perceptual drift. They call it representational drift. Basically, the idea is that even for the same stimulus, it's not the case that the implementation actually stays the same. Which, it's not the same as saying that the memory is indeterminate, but somehow it fits into the same kind of ballpark.
Yeah, I think it's consistent with the things I'm saying. And yes, the neuroscience studies are concerned mostly with anatomical, functional models and also with animal models. But in general, they say little about the actual code and how the actual representation is implemented. And that's where computer science comes into place, because we are interested in actually building devices in which the memory information can be stored and retrieved, okay, in a way. And in psychology, in cognitive psychology, of course, there is a huge literature on memory. But then, the experiments, as you mentioned, assess the phenomena, but again, there is a lack of specifics about how the format of representation and the way the operations are defined. So there's a gap that has to be filled, okay? And I think my impression is that most neurosciences approaches, especially or possibly psychological assessments, still think very much in terms of Hopi model because it's the best that there is, okay? So it's what the, but as I said, for the reasons I said, the Hopi model, it does has limitations in terms of actual natural memory, as I mentioned. Okay.
It depends a little bit also where your target is, right? So you mentioned the declarative memory as one of the ones where it doesn't do well, possibly. But then declarative memory is also a very special kind of memory that, you know, only comes on the scene in, you know, humans of a certain age, basically. And, you know, we're not really sure about other species, whether they do have this kind of memory. So
yeah, of course, I mean, the declarative memory, well, is associated to working memory and the executive functions and all that. But I think it's clear, I mean, that there is a model, I think there is a strong argument support that is a declarative memory module that is different from the diverse forms of procedural memories,
right,
that the ones are using abilities or
right.
like riding a bicycle or playing the piano, in which I mean the information is not rich. These machines are trained, you see, and rehearsed through rehearsal, and they are called memories. I think probably in a kind of accidental way. I mean, because the traditional notion of memory had to be with information that is learned, facts, language, and all that. And learning was kind of acquiring this information that could be retrieved. But then later on, it was discovered that people could learn new abilities even when they were deprived from actual declarative memories or the ways to access it, like the famous HM patient, right? Remember that? And then just because abilities could be learned without declarative memories, then they became the notion of procedural memory. Okay, but not because the things were learned in a sense, but the abilities are trained. Okay, and of course, in a full and accomplished cognitive architecture for a developed species, there must be procedural memories, and there is the declarative memory proper. Okay, and in fact, our model, as we showed in the next session, has a support. I mean, because in order to map information from the external world into the primary buffers that are modeled into the actual representations, I mean, there is an ability there. There are, in fact, we use neural network, we use autoencoders in order to provide these representations as the supporting scaffolding for the information that gets into the memory. But one
this
thing,
is something that, yeah, definitely, if you can highlight a little bit this in the next presentation, I think it'll be interesting to look at. It is a topic in the kind of inactive approach to memory that, you know, looking at body memory, procedural memory, and all these kind of like subsymbolic, you know, forms of memory. And then how do we go from there to something like declarative memory, which, you know, you got concepts of truthhood and falsehood like coming in, like saying, you know, did I remember that correctly? Did I recall it correctly? Is it a truthful statement about what happened and so on? Given that these properties then become applicable to that sort of memory, which they don't really come to, you know, learning how to ride a bicycle, it doesn't make sense to say, is that a truthful procedure or something like that, right? You know, so then the idea is that it's actually somehow our linguistic capacities become somehow integrated into our memory capacities, and then declarative memories come out like a hybrid outcome of that. So I'd be very curious to see how, you know, given that we're also working with like Hopfield style models in our unit, you know, and there's a question of how we can scale them up. It would be very interesting to see how you guys are working on that part.
Right, yes. So I wanted to do this talk first because just to give you the intuition, or the overall intuition of the enterprise. And later on next week, I'll talk about, first of all, the actual computational architecture that we're using, the level, the level of the representational levels that are involved, the machine that performs the translation from the model representation into the actual structure. We call it the analysis machine, which could be seen like the perceptual machine, and also the inverse machine that renders the abstract structures into actual model structures, which is the synthesis machine, or could you be the motor or action machine. So this is the framework that we have, the architecture of the system, and then we have run experiments to store information and to recover information and measure the capacity of the memory registers and the precision and recall on the different conditions of memory, on entropy, and the kind of objects that are rendered back from the memory. And in fact, it's an interesting distinction between what you get when the information is just processed through the neural networks, like the autoencoder, without the memory, which would be like an ability to reproduce an object, and what's the difference that you go through the actual memory, declarative memory place in which you store information and then you recover late information. So all that is the subject of the next talk with the experiment we've done and the results we have at the moment.
Okay, great. So that's just one comment before I open it to the rest of your audience. Was, you use the word architecture, and that I think it will be another interesting thing, because one of the problems that, let's say, an embodied approach has is that it's very hard for us to draw architectural diagrams, because everything is mixed, everything is complex, everything is interdependent. So it's hard to make boxes and connect things and so on. So, but it's something that maybe we should aspire to do more, to have a more clearer diagram of how all the things fit together and what we're thinking about. So it'll be interesting to see how you guys diagram everything. Andres, did you want to say something? I saw you turn on your camera, or no? Tesh, maybe you? I mean, this is closely related to the project that you're working on, so.
Yeah, I think my questions are more of a technical one, so maybe they'll be more relevant to the next.
Yeah, that's okay. I mean, I think that we can probably probe a little bit deeper into your model. It would be better to do it after you present, what you guys are working on in your experiments. Does anybody have a more general question at the moment?
Perhaps just one question, if you have time. I wonder if you have some sort of memory forgetting algorithm.
Forgetting, good question.
Well, there's a discussion on that. I mean, because at the moment, the basic model does not include this forgetting algorithm, but the model that is weighted, I mean, in the sense that the value of the cells are increased, I mean, has an implicit way of forgetting, because the cells that are strengthened are going to be recalled more often, and the cells that are not strengthened are not going to be recalled just because they have a low load. And there is this forgetfulness, but not because we explicitly take the value down these cells. Okay, and of course, I mean, forgetfulness might be due to failures in the hardware and the supporting units, and that's, I suppose, is one of the factors in natural memory that we are not modeling. But nevertheless, the distributed representation, one of the things of the distributed representations is precisely that you might allow failures because the representation is distributed, and even if some parts are damaged, the overall behavior might be sustained. Okay. Now, this question of forgetfulness in neural networks, I mean, probably, I think my feeling is that there is this influence from the short long-term memories networks that have this explicit thing that, I mean, if you prune the values of the network in order you get better performance, okay? And I'm not so sure about it, because one of the, whether you are studying the forgetfulness phenomena at the functional level, And this is different from the actual algorithms that make your machine to have a better performance. That is what happened in long, short-term memories, okay, neural networks. Okay, but nevertheless, here Noé, that is in the meeting, is doing his PhD in this particular model, and he is interested in looking at an explicit mechanism of forgiveness in our model. And we are just starting talking about it. I'm not so sure exactly how would be implemented. The motivation, I see the inspiration, perhaps are also the long, short-term memories, and it is possible. It is possible that if you look at the memories that we're getting in the experiments are huge. I mean, in the basic experiments, these registers are 64 by 64, and entropies are like 3, 4, 5. So the amount of functions there are huge. And although the data we have from the corpus are thousands of objects, nevertheless, these objects are pretty few in relation to the whole amount of things in the memory.
I think that maybe we can come back to this question once we have a better idea of your model, because like now you're already going a little bit into the implementation details.
Yeah, the only thing I want to say that it's possible that these networks, I mean, somehow you might figure out how to decrease the value of the cells or put cells in blanks in order to sort of render more kind of prototypical information. So Noé is interested in that. We haven't really achieved that mechanism. And I still have some doubt whether this is going to be a strategy at a functional level, or it would be just an algorithmic technicality to make the thing more efficient, which are, I mean, it's important to distinguish these two levels of functionality.
Yeah. Very good. Okay, thank you so much, Luis. So now we're prepared for your presentation of the model, and so we will connect again soon. Thank you so much for your presentation.
Okay, well, thank you very much to you, Tom, and Tesh, and everyone. I hope it made sense to you, and I'll be happy to answer any questions for email or to get in touch if you'd like to talk about it specifically. We can have Zoom meetings in order to do specifics. And yeah, hopefully next session I'll give you a brief presentation of the architecture, the experiments, and the results, and probably that will give you a better idea of the framework that we are developing.
Okay, sounds good. Thank you so much.
Okay.
See you next time.
Much.
Bye.
Thank you very much.
Thank you. Bye.